This is section 8.2b, matrix operations. Now we've already learned how to do matrix addition, which includes matrix subtraction. We also learned how to do scalar multiplication. And today we're going to learn about matrix multiplication. If A equals Aij is an m by n matrix and B equals Bij is an n by p matrix, the product AB is an m by p matrix AB equals Cij, where Cij equals AI1 B1j plus AI2 B2j, etc. Now, again, this is a complicated way of expressing a fairly simple idea, so you don't need to write this down. But what I do want to emphasize is that we have an m by n matrix on the left. Notice how it's AB. So A is on the left, B is on the right in that product. And we have an n by p matrix on the right, because B is n by p, and that's on the right. And the product AB is an m by p. M by p. Now, I'm going to spend some minutes now explaining all of this. But the one thing that you do want to write down and make sure you understand just from this definition for now is that m by n times n by p equals m by p as far as the orders are concerned. Now, I will go into that again, so you can write it down, but it's going to become clearer pretty soon. Let's say we have a matrix A, -1, 3, 4, -2, 5, 0. And we have a matrix B, -3, 2, -4, 1. And we want to compute the product AB. Well, here is how matrix multiplication works. AB equals, and we go one element at a time. Basically what we do is we take the first row of the left-hand matrix, in this case A is the left-hand matrix, and we take the first column, the right-hand matrix, and we multiply them. So we have -1 times -3 plus 3 times -4. We use the first row of the left-hand matrix and the first column of the right-hand matrix. And that's going to give us the element that's in the first row and the first column of the product matrix. Now, moving on to the right, you see it says -1 times 2 plus 3 times 1. All we did there is we took the first row of the left-hand matrix and multiplied it by the second column of the right-hand matrix. We get -1 times 2 plus 3 times 1. And that gives us the element that's in the first row and the second column, the product matrix. So notice how the rows and columns match. That's the pattern that you're going to follow for matrix multiplication. Continuing with that pattern, next row, notice it's 4 times -3 plus -2 times -4. Of course, the colors indicate which matrix particular numbers come from. And in like manner, now we are using the second row of the left-hand matrix A and the first column of the right-hand matrix B. And so we have 4 times -3 plus -2 times -4. And that gives us the corresponding element in the product matrix. That'll give us the element that's in the second row and first column of the product matrix. Then moving now to the right, we see the numbers 4 times 2 plus -2 times 1. And as you would probably expect, we are using the second row of the left-hand matrix A, and we are using the second column of the right-hand matrix B in order to give us the element that's in the second row and second column of the product matrix AB. And continuing the pattern, we're going to use the third row of the left-hand matrix A and the first column of the right-hand matrix B, 5 times negative 3 plus 0 times negative 4, gives us the element that's in the third row and first column of the product matrix. And the next and final element, 5 times 2 plus 0 times 1, uses the third row of the left-hand matrix A and the second column of the right-hand matrix B to give us the element that's in the third row and second column of the product matrix AB. And our final answer, once we multiply and add everything, is negative 9, 1, negative 4, 6, negative 15, 10. And you can take a moment to prove that to yourself. If you want to do the operations, it would be a good idea just for practice. And also, before you go on to the next screen, you should definitely have that pattern down. You should have the pattern down, have it learned. You can see the pattern, the colors help with that. And that's the pattern that you follow always with matrix multiplication. Now, what I'm going to do next is talk more about the definition and try to do it in a simpler way. The main point of showing you this example with the red and blue numbers is to show you the pattern of matrix multiplication. The order of the product matrix is 3 by 2, and you'll notice that that would correspond to M by P if we're looking at the definition. See, A is M by N, in this case 3 by 2. B is N by P, in this case 2 by 2. And the order of the product AB is M by P, and that is 3 by 2. Now we're going to continue to talk about matrix multiplication and hopefully clarify that definition a bit. You want to write these sentences down. For matrix multiplication to be possible, the number of columns of the left-hand matrix must equal the number of rows of the right-hand matrix. The order of the product matrix is the number of rows of the left-hand matrix by the number of columns of the right-hand matrix. The little X in parentheses next to the word by is just the symbol for by. That's why I put it there, because orders are usually expressed with that symbol, the X symbol. All right, so a little way to visualize this that can be helpful is the following. Let's say we have two matrices. The one on the left has order M by N. The one on the right has order N by P. The dot in the middle means we're multiplying them. Well, the ends are important because they determine the multiplicability of the matrices. They have to be equal. If they're not equal, we cannot multiply the matrices in this order. So the two middle numbers, when we have orders, when we're comparing orders of matrices that we want to multiply, the two middle numbers need to be equal. And the two outer numbers, or the bookends if you want to think of them that way, these determine the order of the product matrix. So recall in the last example that we had a 3 by 2 product matrix because that matched the number of rows that were in the left-hand matrix and the number of columns that were in the right-hand matrix. Okay, let's continue now with a specific example. Let's use our matrix A from the last screen. It was negative 1, 3, 4, negative 2, 5, 0. And our matrix B from the last screen also, which was negative 3, 2, negative 4, 1. And let's try to analyze this definition, especially the two sentences at the top of the screen, and see them in action. All right, so is A, B possible? Is it possible to multiply A by B? Yes, because the number of columns of A equals the number of rows of B. So here we see that the number of columns of A is 2. The number of rows of B is 2. And so those inner numbers of that M by N, N by P definition, those inner numbers match. And the order of the product shown here, AB equals negative 9, 1, negative 4, 6, negative 15, 10. The order of the product AB is 3 by 2 because the number of rows of A is 3, whereas the number of columns of B is 2. And those determine the order of the product matrix. So by the definition, that would be an order of M by P. M by P. Now, we have to ask ourselves another question, though, using the same matrix A and the same matrix B. The question is BA possible? Well, it's not, because the number of columns of B does not equal the number of rows of A. All right. In this case, B is going to be my left-hand matrix, and A is my right-hand matrix, simply because it's BA. And in BA, B is on the left, A is on the right. So we have to treat them that way. Well, if B is now acting as my left-hand matrix and A is now acting as my right-hand matrix, well then I need to look at the columns of B and the rows of A. And as it happens, the columns of B, 2 in this case, the rows of A, 3 in this case, do not match. And therefore, this product matrix of BA is impossible. It does not exist. The very important conclusion from this is that matrix multiplication is not commutative. You might remember from Algebra 1 with the different properties, and you learn that multiplication is commutative, which means, for example, like 4 times 3 is the same as 3 times 4. 2 times 8 is the same as 8 times 2. Well, that is true in arithmetic, but with matrix multiplication, the commutative property does not apply. And AB is not the same as BA. So BA simply does not exist. Now let's look at some examples. We'll use a sample matrix of A, 1, 0, 3, 2, negative 1, negative 2. Sample matrix of B, negative 2, 4, 1, 0, negative 1, 1. And we're going to perform this multiplication, AB, treating A as the left-hand matrix and B as the right-hand matrix. For practice, you should try to do this on your own. But if you get stuck, you can resume the video to get some help. So pause, do this on your own, and then resume. All right, let's go through this step by step. If we want to find AB, first of all, is it possible? Well, we need to look at the number of columns of the left-hand matrix and the number of rows of the right-hand matrix. And yes, they do match. We have 3 columns in the left-hand matrix and 3 rows in the right-hand matrix. So AB does exist. Now, going through the process of finding AB, well, we first need to go to the first the first row of the left-hand matrix and the first column of the right-hand matrix. First row of the left-hand matrix, first column of the right-hand matrix, and we do the appropriate multiplication in order to get the element that's in the first row and first column of the product matrix. And we have negative 5. Let's go through that step by step. Well, looking at the numbers that are circled, 1 times negative 2 is negative 2, plus 0 times 1, still negative 2, minus 3 is negative 2 minus 3, and that is negative 5. So as we can see visually here, we use the first row of the left, the first column of the right, in order to get the element that's in the first row and first column of the product. Continuing now, we're going to use the first row of the left-hand matrix and the second column of the right-hand matrix, and I'm going to multiply those in order to get the corresponding entry of the product matrix, which is in the first row and second column. And that is 7. 1 times 4 plus 0 times 0 plus 3 times 1 is 7. Continuing now, we are going to use the second row of the left-hand matrix, the first column of the right-hand matrix, in order to get the element that's in the first row, the second row and the first column of the product matrix. And that element that's in the second row and first column of the product matrix is -3. 2 times -2 plus -1 times 1 plus -2 times -1 is -3. And finally, we will use the second row of the left-hand matrix and the second column of the right-hand matrix. We're going to multiply those in order to get the corresponding entry of the product matrix, which is in the second row and second column. Second row and second column. When we do that, we get 6, because 2 times 4 plus -1 times 0 minus 2 is 6. So AB is -5, 7, -3, 6. Okay, now you should calculate BA. Again, pause the video, calculate that on your own, and then resume when you have an answer. And BA is 6, -4, -14, 1, 0, 3, 1, -1, -5. Now, one thing you can do is check these on your calculator. You should have already found out how to use your graphing calculators to perform Gauss-Jordan elimination on a matrix. Well, you can also use your calculators to perform simple matrix multiplication. And most calculators allow you to create a matrix A and create a matrix B. And then you can simply multiply them, do AB and then try BA. You should know how to do these by hand, but you can also learn how to do them by calculator, especially to check your results. Another example, A equals 2, 3, -4, 7, 19, -1. B equals -2, 3, 1, 0, 1, -2, -1, 10, 6. All right, and we want to find AB, the product AB. So you first need to ask yourself, of course, is this possible? Well, you need to look at the number of columns of the left-hand matrix and the number of rows of the right-hand matrix. Is it possible? No, it is not possible, because those numbers don't match. We have 2 columns in the left-hand matrix, and we have 3 rows in the right-hand matrix. Therefore, they are not multipliable. How about BA? Is BA possible? Well, pause the video, decide that for yourself. If it is possible, calculate it, and then resume. Yes, it's possible, and this is the answer. 314, -42, 9, 72, 61. And again, this is something you should do by hand, and then you can check your results with your calculator. Another example, matrix A is 2, 1, -4, 0, 1, 3. Matrix B is 3, -1. AB, is it possible? Yes, it is possible, and you should pause the video, find it, and then resume when you have an answer. Five, -12, 0. Notice how the product matrix has the order that is given by the number of rows of A and the number of columns of B. Number of rows of A, 3. Number of columns of B, 1. Therefore, 3 by 1. AB is a 3 by 1 matrix. How about BA? Is BA possible? Pause the video, decide for yourself, and then resume. No, it is not possible. It is not possible. BA does not exist. And it does not exist because if B is now acting as my left-hand matrix, because it's BA, B is on the left, and A is acting as my right-hand matrix, because it's BA and A is on the right, well, the number of columns of B does not match the number of rows of A, and therefore they are not multipliable, and the matrix BA does not exist. Alright, here's a typical word problem involving matrices. A local softball club has 4 teams: women's, men's, boys, and girls. Bats cost $80 each, balls $6, and gloves $60. The quantities of each item of equipment are, okay, and then you can see this table: women's team, men's team, girls team, boys team, columns, and then the rows: bats, balls, gloves. And we can see how many of each type of equipment each team has. Alright, so the question is, use matrix multiplication to find the total cost of each team's equipment. Alright, now obviously you could do this manually and just multiply the numbers accordingly. You could do that. But there are 2 reasons we want to use matrix multiplication. First of all, of course, is because we're trying to learn about matrix multiplication. But the other reason is when you have complicated matrices, it becomes very tedious to do it all manually. And not only is it tedious, but it's prone to error because you're doing so many operations. So the best thing to do in these cases is figure out the appropriate matrices, and then you can just do them by hand and check them on your calculator. Alright, so let's try to solve this word problem using matrix multiplication. Well, we can call the equipment matrix E, and E equals 12, 15, 14, 16, 45, 38, 40, 43, 15, 17, 13, 18. Alright, that is my matrix E, equipment matrix. And I can come up with this cost matrix C equals 8660. Alright, well, that's kind of a logical place to start, but you need to be careful. You need to be careful. Notice the problem doesn't tell you whether to set up a column matrix or a row matrix. So this is just kind of your first guess. But how do you check? Well, you check simply by asking yourself whether the product EC is possible or the product CE. And actually, EC and CE are both impossible. Now we know that the matrix E is right, but the problem is going to be with our matrix C. Okay, so the point of doing this, and the point of putting it the wrong way first, is I just want to show you that it's okay to just take a stab at it. You can always test by seeing whether the matrix multiplication is possible. If it's not, then you need to adjust your matrix. Alright, first before we go on, why is it impossible to get the product EC? Well, if E is my left-hand matrix and C is my right, the number of columns of E4 does not match the number of rows of C, 3. 4 is not equal to 3, therefore that's impossible. How about CE? Well, CE treats C as the left-hand matrix and E as the right-hand matrix, and the number of columns of C, 1, does not equal the number of rows of E, 3. So CE is also impossible. Therefore, we know that we need to adjust C. We need to adjust C. And here's how we adjust C. Alright, E is fine, we just rewrite that, but C needs to be a row matrix. I'm writing 8660 in this way. And then we proceed. Alright, we know that we want to multiply these two matrices. The question is, which order? do we want EC or do we want CE? Well, you simply need to see which one works. Does EC work? Well, treating E as the left-hand matrix and C as the right-hand, if I look at the number of columns of E, that's 4. The number of rows of C is 1. That doesn't work. So it's not EC. But CE does work because treating C as the left-hand matrix and E as the right-hand matrix, the number of columns of C is 3, the number of rows of E is 3, 3 equals 3, therefore CE is possible. Alright, now you should pause the video, calculate CE, and then resume when you have an answer. So C is of order 1 by 3, E is of order 3 by 4. The product CE will be of order 1 by 4. Remember that the order of the product is determined by the number of rows of the left-hand matrix and the number of columns of the right-hand matrix. And so we get CE equals 2130, 2448, 2140, 2618. All right, now the temptation that many students have is to think that they're done once they get a matrix like this. The numbers are correct, but this is still not a complete answer. And it's not a complete answer because it's a word problem, and you have to express it in words, or at least concepts. Okay, and the hardest part about matrix word problems is getting the units straight. Okay, so let me explain what I mean by that, and you want to write this down. Just as the number of rows of the left-hand matrix determines the number of rows of the product matrix, and the number of columns of the right-hand matrix determines the number of columns of the product matrix, likewise the units, or type, of the left-hand matrix's rows determine that of the product matrix's rows, and the units of the right-hand matrix's columns determine that of the product matrix's columns. So let's look at this specific example. We are calculating the product CE, and that, according to that, C is my left-hand matrix and E is my right-hand matrix. And we know that the number of rows of C, since that's on the left, determines the number of rows in the product. So there's only going to be one row in the product. And the number of columns of the right-hand matrix, which is 4, determines the number of columns of the product matrix, which is 4. Okay, but we also need to look at the units of what these numbers represent. Well, the left-hand matrix, that 8660 matrix C, which I'm considering my left-hand matrix for the product CE, the units of those numbers is dollars. And in my right-hand matrix E, the units of those columns is type of team. And therefore, the correct way to express this answer, the answer to this word problem, would be a table. Okay, your matrix is there, 2130, 2448, 2140, 2618, but you need to write the properties, the units. And those are determined by the sentence that appears on this screen, just as the number of rows, etc., that long sentence. Well, it's gonna help to remember that, a long sentence, or at least understand it, and then do it by feel as you go in these word problems. Because getting the numbers is only half the battle. You also have to be able to say what those numbers mean. Alright, so if we write it as a table, notice that we get dollars as the units for the row, because those were the units for the matrix C. And we get type of team, women's, men's, girls, boys, as the units of the columns, because those were the units of the columns in E. Alright, and so what that means is the women's team has $2,130 of equipment. The men's team has $2,448 of equipment. The girls' team has $2,140 of equipment, and the boys' team has $2,618 of equipment. The classwork, page 598, please write these down. The little notes next to 57, just solve. That'll become clear in class. Basically, I just want you to do a certain portion of that problem. Please write these down, get a head start if you like, and then we'll work on it in class.